Thank you, Meg, and thank you, Sarah, and thank you everybody for inviting me to be here and to talk with you guys today. I'm really excited to talk with you. Meg has told me about your group and what you're doing, and I think it's fantastic that you're working together on a regional and national and even international scale. It's really fantastic to have the opportunity to learn from each other on different scales like that. So like Meg was saying, I am a coastal geologist with the South Carolina Geological Survey, and I am going to go ahead and try and share my screen, make sure you guys can see my PowerPoint presentation. And so I've worked with the Geological Survey since 2014, and I'm based in coastal South Carolina and Charleston, South Carolina. So I really have the good fortune of working on a lot of really interesting coastal projects dealing with modern coastal dynamics and geomorphology. And in recent years, everything we work on has just become incredibly interdisciplinary, giving us the chance to collaborate with a lot of different researchers, not only within South Carolina DNR, but also working with different institutions and universities in South Carolina and sometimes also in Georgia and North Carolina, which is great. So today I am hoping to talk for maybe 45 to 50 minutes and give some time for questions at the end. But I'm going to be covering sort of coastal geology in a broader sense. So putting things in the context of geology and Earth history. I think every geologist I know, I enjoy talking about sort of like deep time. So I'm gonna give you a little bit of that early on in the presentation, and then we'll talk about our modern coastal setting and the different physical factors that are impacting why our coast looks the way that it does. And then I'm going to specifically start talking about our project out at Quantifying Island and why we're so interested in working out there and in other sort of erosional hotspots along the South Carolina coastline. So starts you off with a picture that I'll be showing later on in the presentation as well. This was taken at the end of January of this year. This is, I think, part of Quantifying Island shell ring #1. So we're going to talk about why you see some dead trees in this picture and how much erosion has happened at that site just within the past couple of years. So starting off with geology in a longer and larger context, and trying to think about putting where we are currently in the context of that longer Earth history. The Earth originated 4.5 billion years ago, to the best of our knowledge, and to the best of sort of what the rocks tell us. And what's kind of amazing about that is that so many of the things that happened in Earth's history that have an effect on the way that our North American continent looks today and the way that our South Carolina coastline looks today happened within just a teeny tiny fraction of that 4.5 billion years. So this graphic is a great example of a way of visualizing that span of Earth history. Another thing that I really like to do, and this is more effective, I think, when I'm actually in front of an audience, but I'm going to try to do it today with you guys. If you hold your arms out to both sides and imagine that this entire span between the end of your left hand and the end of your right hand represents all of Earth history, so 4.5 billion years. The time encompassed in everything that's going on here, so Pangea, the age Cretaceous, so the age of the dinosaurs, and then our, moving into our modern Earth history would fit in the palm of your right hand. So, and then our modern sort of human history would fit in the very end of the fingertip on your on the middle finger of your right hand. So, in the context of larger geologic history, what we're going to be talking about today is very, very young geology, but it encompasses so many things that have led to the way that why our coastline looks the way that it does. So Today, I'm going to be focusing not on all of Earth history, which may be a relief to you guys because there's a lot, but really on what's happened starting with about 100 million years ago, so back during the Cretaceous. So during the Cretaceous, just to give you an idea of, things have changed a lot, continents have moved a lot in the past. One really important takeaway, I think, that I try to instill in people is that shorelines have also moved, and our shoreline and the level of the ocean has been in different places over time as well. So if we think about that time during the Cretaceous, about 100 million years ago, dinosaur sort of prime time, the planet was quite a bit warmer than it currently is today. CO2 levels were at least twice what they are today, so maybe between 800 and 1,000 parts per million. And you can see this sort of black hatched line here. The shoreline ocean levels were a lot higher. There was no glacial ice anywhere on the planet, and ocean levels would have been right about where Columbia, South Carolina sits today. So it sort of would have followed this black hatched line here. And so starting at 100 million years and then moving forward through time into a period that we call the tertiary. So around 65.5 million years ago, extinction of the dinosaurs, you can see that shoreline, as we move towards modern times, is going to fluctuate quite a bit. And so what we are going to be focusing on today is really what's been happening since the last glacial maximum. So starting in the Pleistocene around 2.6 million years ago, we entered into this period of time where we experienced glacial periods where ice advanced onto our continents, and then interglacials, which were warmer periods. We're currently in an interglacial right now, warmer periods where that ice retreats, melts, sea levels rise. So our most recent glacial period, the last glacial maximum, or LGM, peaked around 21,500 years ago, so end of the Pleistocene. And our sea levels were much lower than they are today, so about 120 meters lower. So our shoreline at this point in time was pretty far out on what we call the continental shelf today. Things started transitioning really around 18,000 years ago, and that ice started retreating, melting. A lot of the water that was tied up in those glaciers was released into the oceans, and our sea level started rising. And that sea level rise continued. The pace of it was pretty rapid at times, but we think that things started to kind of slow down and stabilize, and sea level started reaching something near their present levels around 4,500 years ago. And that's what really allowed our modern coastline and barrier island dynamics and marsh dynamics to sort of set up, was this lower rate of sea level rise. So to give you kind of a view of what that looked like on a continent scale, I have a series here taking us through the Cenozoic, which is our most recent geologic era. So this is starting around 65.5 million years ago. And you can see as we toggle through the Paleocene and the Eocene, that sea level was still pretty high here. And during the Eocene, we would have had some carbonate rock depositing off in our current day coastal plains. So we have a formation called the Santee limestone that was formed during this time. We also have a lot of carbonate forming in Florida and on the Bahamas platform, and that continued through the Oligocene. In the Miocene, things became a lot more sort of arid and dry on the continent. And then starting in the Pliocene, we started experiencing the first of these ice ages, where we really had glacial activity, first starting in Antarctica and then in the Arctic. So as you can see, this is a glimpse of sort of what that ice sheet would have looked like during the last glacial maximum around 21,500 years ago. So it would have advanced down about as far south as Long Island, New York, and then retreated and left behind very distinct morphologies that you can see in places in New England, places like Acadia National Park. So these glaciers had a big influence on the local landscape, but they also had a big influence on sea levels. So in cross section, just kind of to give you an idea of sort of where the ages of the sediments that we're going to be talking about today. So this is a little schematic of South Carolina, and you can see that South Carolina is split broadly into 3 geographic provinces. We have Blue Ridge up near our border with North Carolina, Piedmont, and Columbia is right about here along the fall line. And then the rest of the state, so a big proportion of the state is made up of the upper, middle, and lower coastal plains. And so up near Columbia, if you'll remember back to that, that map with the shorelines, the shoreline around 100 million years ago was right about here, right up near Columbia. So we have our oldest coastal plain sediments outcropping near Columbia, and those sediments are going to get progressively younger as we move west towards the coast. So in this middle part of the coastal plain, we have tertiary rock, so 65.5 million years to about 1.8 million years in this zone, and then towards the coast, this is all Pleistocene and then Holocene sediments. And then when we get to our barrier islands, they are quite young. So on the order, definitely Holocene, on the order of usually a couple thousand years old. So our modern coastal setting is part of a larger area that South Carolina is part of a larger area that we call the South Atlantic Bight. And it's a curved stretch of coastline that really goes from Cape Hatteras in North Carolina to Cape Canaveral here in Florida. And you can see here that we have, this is the shelf break right here. So this is in feet. So this is a 500-foot bathymetric contour. And you can see that the shelf really, really narrows as we get down towards southern Florida and up towards the Outer Banks, but it's really broad here in South Carolina and off of Georgia. And so that curvature of the coastline really focuses our tides, giving us what we call a mesotidal tide range, which is between 6 and 12 feet. And in South Carolina, in central and southern South Carolina, it's more on the order of about 6 feet. The tide range gets bigger as we go south into Georgia. So we have a middle of the road tide range. We're not microtidal. Anyone familiar with the Gulf or Florida or the area around the Outer Banks probably knows that the tide range in those places is a lot less than what we see in South Carolina, but we're also not macrotidal. So definitely not anything like the Bay of Fundy here. But so we have sort of middle of the road tide range. You can see that here in this chart. Here we are in sort of central South Carolina. That tide range is going to increase going south into Georgia. And we also sort of have mid-range wave heights. So what this does is it really sets us up to have conditions that create a mixed energy environment where both the tides and the waves are intermediate in size. And so the result of these conditions is really what we see along the central and southern part of the South Carolina coastline, which is short, sort of drumstick-shaped barrier islands. And I'll show you some examples of a drumstick-shaped barrier island in a couple of slides. And these barrier islands are going to be backed by tidal flats and coastal wetlands. They are separated from one another by tidal inlets. And then we also have very complex sediment distribution patterns. So something that's happening, in a pattern of erosion that's happening on one island could be completely different from the island that's, down the coast from it. And a lot of that just has to do with the separation and the impact of the adjacent inlets on these islands. And then also importantly, our sand moves through a longshore transport system that generally takes sand from north to south. And so there are a few exceptions to this rule, but generally sand is moving from north to south. And just as a sort of diagram showing this longshore drift and longshore transport system. So this is really driven again by the wind direction and the dominant direction of the waves, which is coming out of the northwest. And so those waves are driven onto shore, and they tend to pick up sand and sort of move it up the beach and then down, up the beach and then down. And so over time, if you have a grain of sand on the beach here, it's going to move in sort of this zigzag pattern down the beach. So a grain of sand on an island is going to move south and then eventually hop over to the next island downdrift and move that way. So that is predominantly how our sand moves along our coastline. And so you might be asking yourself, what does this all have to do with archaeology? Well, if we think about the time that we have since the last glacial maximum, so about 21,500 years ago, there's a lot of interesting evidence offshore of just old channels, old deltas, iceberg scours, different features like paleo channels that we pick up in bathymetry data. And over here, this is from a paper by Harris et al. In 2013. And you can see off here. So this is all data that's been collected by NOAA as well as by universities like Coastal Carolina University and the College of Charleston. So there's a lot of evidence that these environments were exposed and that people may have inhabited these areas and lived out here. One interesting thing about paleo channels, so these are old channels that were in sizing. Back when the shoreline was out here way at the shelf edge and all this area was exposed, we had channels coming off onto the modern day continental shelf in sizing, and we can pick those up in geophysical data and seismic data. And as the water sort of advanced, these paleo channels refilled with new sediment. And so up in the northeast, they've targeted some of these paleo channels for beach renourishment resources, but there is definitely a conflict of interest because Native Americans also see this as, potential heritage sites. So paleo channels are a really interesting feature that we pick up in the geophysical data. Again, we also see in the bathymetric data, and this is sort of a location here of where this is located on the shelf. This is, I think, data collected by the College of Charleston. And you can see this really well-preserved channel offshore. And then further out on the shelf edge, they've even picked up iceberg scours. So there's a lot of evidence of things going on out on the shelf that indicate that it was subaerially exposed at one point, and that, things may have been pretty similar to what we see in our modern day coastal plain. So I'm going to transition to talking about Botany Bay Plantation Heritage Preserve for the rest of the talk, but I think there's an interesting connection between thinking about what's going on offshore and then thinking about the Pocky Island shell rings, because they represent this heritage at risk of being inundated by the ocean, and that is already what's happened to a lot of things that are currently off near shore and offshore. So it's definitely a really interesting and dynamic place to study and work. Botany Bay Plantation Heritage Preserve is a South Carolina DNR wildlife management area, and it's located about an hour south of Charleston. And I find it to be a really neat place because it's an area where geology, coastal geology, has really been allowed to do its thing. There are so many areas of our coast where we have development, and we have, we're trying to protect houses and businesses and developments, and coastal engineering techniques like renourishment and the use of jetties and groins has kind of altered our sediment dynamics. But this is a place where erosion is happening and it is completely natural, and we get the chance to see it in action. So I think sometimes it can be a little distressing to people to see how much it's changing, but it is really, really interesting to be able to watch it happen and see new things every time we go out there. So I'm going to be marking some of the photos that I show you and maps that I show you with these white stars, and this is just going to indicate sort of a red flag that we think about when we see something that tells us this area is eroding and rapidly. And so in the instance of this picture, that evidence is this outcropping substrate here, which I believe this was a relic marsh here. So whenever you see any sort of marsh mud, estuarine sediments outcropping on a beach, it's a good indicator that the island or the shoreline is transgressing or moving landward and sort of rolling back over itself, and that sand is being pushed back into old environments. So this is something that is somewhat common on some of our eroding barrier islands, but I'll be mentioning a few more sort of red flags of, hey, if you see this, it probably means there's quite a bit of erosion going on where you are. So to give you a better context of where exactly we are, we're in coastal South Carolina right here, and Charleston is here about midway down the coastline, and Botany Bay and Quawah Island are located about an hour south of Charleston on the northern part of Edisto Island here. So Edisto is bounded by the North Edisto River and its inlet right here, and the South Edisto right here. And then we have various barrier islands to the north. This is Kiawah Island. Kiawah is a good example of a drumstick-shaped barrier island that I was mentioning earlier. Another good example of a drumstick-shaped barrier island would be the Isle of Palms, which is right here. So you can see these islands are sort of thicker at their northern extent, and then they kind of thin out as we go towards the south. In the case of Kiawah, there's a spit at the southern end. And so Botany Bay is a property that has been managed by South Carolina DNR since 2008. Prior to that, it was privately held, and it is a very popular place, sort of an off the beaten track kind of place for people to come and visit. You can see these visitor numbers are pretty impressive, and most of the people who come to the property go out to see the beach because it is a very unique beach. It's very different from visiting Kiawah or Folly Beach or Isle of Palms or anywhere like that. And it's also a really important beach from an ecological standpoint. It's an important shorebird habitat. It's also an important nesting beach for the loggerhead sea turtle, and of course the site of 2 known Native American shell rings. So it's really a very compact, very interesting area, and presents a lot of opportunities for us from not only a public outreach perspective, because so many people visit the property, but also from the standpoint of managing it for habitat, and also the excavations that have gone on there the past few years, which have also involved members of the public and had a educational component to them. So I think there's a really neat synergy with the property and everything that it sort of offers, and definitely a feeling that we need to study everything as quickly as we can because it's eroding so fast. So we really started with the geological survey, really started getting involved out at Quawah in 2017. And we were getting emails from some of the DNR land managers out there. They have volunteers on the beach who interact with members of the public and try and describe, what's going on the property, why the beach looks the way that it does. If you had gone out to the beach in 2017, you would have seen something that looks kind of like this. So this is Pocky Island right here. And then there was some interesting stuff outcropping on the beach. And the land managers were used to seeing, you know, estuarine sediments and marsh, relic marsh deposits on the beach. That was a pretty regular thing. But what was outcropping at that point in time was sort of this cemented, oxidized, iron-rich sand. And then in certain places, there was a really distinct contact between that and kind of a green clay layer. So their question to us was like, what is this? Why is it here? And what do we tell members of the public? So we went out, we looked at some historical maps that we had, and we, once we got out there, it became pretty clear that what was happening was that the erosion had gotten so bad that it was actually incising into Pocky Island. And so Pocky is, for a long time in its history, was what we call a hammock island. So it was set back from the active beach face. At one point in time, when Pocky was first formed, it was the active beach, but it has not been at the shoreline for thousands and thousands of years. So what was happening was that the erosion was actually sort of down cutting and eroding into these sediments that were underlying Pocky Island. And these were, so Pocky was originally, when it was originally formed, it would have been beach, sort of barrier island deposits. And so all this sand, when it was, you know, there's also groundwater that's helping to keep this maritime forest alive. So you think about groundwater sort of percolating through that sand over thousands and thousands of years, it's cemented it together. And then when it's re-exposed on the beach, it has a chance to oxidize and turn this sort of distinct orange color. So it was a really interesting sort of exercise, because it was the first time that we had seen that on one of our coastal properties. So just to give you an idea of what we have in terms of our historic maps of the area, and sort of what we went to first when we were looking at, you know, trying to understand just how much erosion had happened in relatively recent time. This is an 1851 historical property map that was done by the U.S. Coast Survey, and there's a transparency on it, so you can see through to some 2019 imagery. So this imagery shows you what the island looked like in 2019, overlain by this historic map. And if you go out to the property today and you want to go out to the beach, you'll come into the property, you'll park right about here, and there's a causeway that takes you, sort of a walking path that takes you out to the beach. And so the modern day beach is right about here, and Pocky Island is right here. But you notice from the historical map that causeway used to go out almost a kilometer past where it currently is. So the beach in 1851 was way out here. Pocky Island at the time was a hammock island that had likely been isolated for thousands and thousands of years from direct impacts like tides and waves. So this really gave us a good sort of overview of how much erosion had happened within a more recent human time span. We also had quite a bit of historical imagery sort of in-house. So our first step after that was to come up with a long-term shoreline change rate so that we could kind of understand how much, quantify, put some numbers on how much erosion had happened over time. So we had the 1851 map, but we were interested in looking at throughout the 1900s specifically. So we started with a 1949 shoreline, and this image here is a 1949 orthophoto. So we digitized the wet dry line on a series of these photos, this one from 1949. We also had a 1973, a 1989. This is a 2006, a 2013, and a 2016. So we were doing this work in 2017. So we ended with a 2016 image that was collected, I think, after Hurricane Matthew. And what we found is that between 1949 and 2016, we had lost, at the causeway, we had lost 500 meters or 1,640 feet in total for an average rate of about 7.5 meters or almost 25 feet of erosion per year, which is just absolutely astronomical in terms of erosion rates along our coastline. It's much more common in eroding areas to have rates on the order of several feet per year, but double digits. Erosion, absolutely remarkable. Another thing that's interesting, and so here's another one of those stars to tell us that there's kind of a red flag here to tell us that there was bad erosion happening even back in 1949. On this image, you can see evidence of something we call overwash. So this happens when you don't have a really nice established primary and secondary dune system. And so during storms, what happens is the sand from the beach gets pushed back and washes over these sort of estuarine environments. So this is all salt marsh here, and you can actually see some of it outcropping on the beach here. So even in the 1949 imagery, we see some very clear evidence that erosion was happening, and it was happening quickly. And you can see here also from 1949 to 1973, there was just quite a remarkable bit of erosion going on. So you might be asking yourself, why is this happening? Why is this such a erosional hotspot? Well, there's been some research done to investigate this, and we think that it all goes back again to those inlet dynamics and that compartmentalization that we talked about earlier in the presentation. So we have evidence through the 1851 map that the island was healthy at one time. It was actually building, it was regressive, it was building outward towards the ocean. And then at sometime in the late 1800s, based on the maps we have and bathymetry charts, things seemed to go south, and something happened, and it became a transgressive or eroding barrier island. So we have some evidence from NOAA bathymetry charts that this inlet here at the North Edisto, actually, it used to sort of dogleg here in the mid 1800s, and in the late 1800s, kind of straightened out. And this happens sometimes. Sometimes channels reestablish in old former locations, because if you think about what things looked like when the shoreline was way out on the continental shelf, we had channels, and they incised in different places. So sometimes our modern day channels will reoccupy an old location that may be deeper than another way that it was going at one point. So we think that the North Edisto Inlet probably reoccupied an old part of its channel. Now this is significant because these inlets bring sand to our coastline. So our beaches are naturally renourished through sand that originates from the Piedmont and upstate from the erosion of rocks, and all that is carried down our river systems through our inlets. And what happens is that sand is sort of entrained in the ebbing or falling tide. And then when it meets that longshore transport, it drops out and it forms these features that we call ebb tidal deltas. So right here at the mouth of the inlet is just a lot of sand. And that sand is what naturally renourishes our beaches. So over time, that sand gets pushed by waves onto the adjacent beach. But since that inlet was depositing sand so much further offshore, what we think was happening is that the sand was being trapped before it could be transported south. You'll also notice this feature here. So this started off as a spit. This is DeVoe Bank. It's currently a really important brown pelican nesting habitat. As you can imagine, it offers great protection from predators, and it has grown substantially in the past few decades. So while Pocky, located right here, has eroded heavily, we've seen a lot of growth of DeVoe Bank. So it seems like the sand is getting sort of tied up here in the ebb tidal delta. It's nourishing DeVoe Bank. And any sand that's making it onto Pocky is either moving south in the longshore transport system, or it's actually being directed north, because there's a reversal here from waves being refracted around the uptidal delta. So this delta, again, is massive. Waves hitting it coming out of the northeast are going to sort of refract around here and carry sand either up to the north or down to the south. So this is a diagram from a paper that came out in the 1990s, kind of showing another view of this. So here's Devoe Bank, here's the North Edisto, here is our focus area Pocky, and you can see the transport is north here and it's south here. So sand, if it's making it to the Pocky area, it's just not staying on the beach, unfortunately. And without enough sand, these systems can't really build effective dune systems to protect themselves against high tides and storm events. And they become impacted from the waves directly. So this is just a visual to kind of help you see what that looks like over time. This is a great tool that I really like to use, and I really recommend if you're interested in looking at land use changes, coastal geology, glacial retreat, anything that you could benefit from kind of viewing like a year by year view. This is something that Google put together with Landsat Imagery. So this is 30-meter resolution imagery. So it's not insanely detailed, but it gives you a really good sort of overview of processes that are going on. So we're going to start in 1984 and we're going to end in 2018. And I'd like for you, so here again is Pocky, that causeway is right here. Pocky Island is right here. This is Devoe Bank. This is the North Edisto. So keep an eye on what's going on the north end of the island at Devoe Bank. And then also, I'll loop it through a few times, but keep an eye on what happens at Pocky as well. So starting in 1984, you could see that sand accumulating here at Devoe Bank, and the northern end of the island actually growing. But here at Pocky, you can see lots of overwash here, and you can really get a clear idea of how much erosion was happening over that time period. So we first got involved in I think early 2017 to help explain what was going on the beach. We also became more involved with Meg and Karen and Sean and the rest of the archaeology team when the Pocky Island shell rings were discovered from NOAA LIDAR that was flown after Hurricane Matthew in 2016. So this is a LIDAR derived image that many of you I'm sure have seen, showing the outline of Pocky Island here. And then very distinctly, you can see shell ring number 1, shell ring number 2. Another really interesting thing I think you can see from this LIDAR is sort of that colonial past of the island when it was ditched. I believe this was planted for cotton, and you can see sort of the relics of that, which are definitely not apparent at first glimpse when you're out on Pocky Island. And this is a image that was taken by Jamie Kolker in 2018, showing the excavation site here. And so you can see that this is just, it's a challenging place to work at high tide. There's really not much beach to work with. And then of course, we've seen quite a bit of erosion since this time. Another star, so you've seen this in a few other photographs I've shown you so far, but another indicator that we have an eroding or transgressing barrier island is by seeing, if you see trees on the beach, trees in the water, it's an indication that we're getting erosion into a maritime forest environment. And that's what we call a boneyard beach. So, there are other places in South Carolina where you can see this happening. Hunting Island, Capers Island, sometimes the northern part of Folly Beach. And I would bet along other stretches of coastline where you all work, you also see some of this going on. So Pocky is a really fascinating place to work. It's a place where we have become just more and more involved over the past 4 years. And so we've developed over time some sort of overarching goals that have been steered by the work of others, as well as some funding that we have gotten. Our number one priority from the beginning was to create outreach materials that could be used by South Carolina DNR researchers and members of the public. And so we've done that through seminars and training sessions with volunteers, trying to help them communicate to the public why the beach looks the way that it does. We've also created outreach materials, such as an online Arctic story map. We've created one of those in 2017 to explain the coastal geology of the area. And if we have time at the end of the presentation, I'll just show that to you quickly in a web browser. And then more recently, we've created another a mobile app that people can actually use when they're out on the beach. And I'm going to show you a couple of sort of snippets from that in a few slides. Over the past few years, we also developed some objectives to try and help frame the area in more of like a longer term paleogeology and geologic context. So trying to imagine what how old the area is and maybe what it looked like when the shell rings were being created. And then most recently, so what I'll talk about last are our efforts to document the short-term erosion rate and the possible impacts of other things that have come up as erosional drivers like king tides. So this is first of all, I'm going to talk about the mobile app that we created, and Esri really has some neat tools that we were able to take advantage of. And the first thing I thought of was, I don't know if any of you guys, I think Meg is a Friends fan. If anybody else that knows the TV show Friends, I thought about this, actually trying to get people sort of into the map in a way so that they could imagine where they are located when they're out at the beach in the context of some of the older geology. So we put together, this is part of the web app. People can go in here and they can look at these old images, ortho images from 1949, and shoreline locations. So this is 1973. So it flips people through the imagery. And you can see here again is Quawah Island. So in theory, they would be on the beach located right around here. And they would be able to see also all of these shorelines and locate themselves in terms of these old historic shorelines and images. And one really neat feature about the mobile app is it's called the locate tool. So if you have good enough cell reception, you can click this tool and your phone GPS will actually kind of pop up and put you at your location. It's sort of a pin, so you can see where you are, and you can see where you are in the context of some of this older imagery and these shoreline positions. And so we've also, this is another part of that mobile app, and this is just a comparison between the 1949 imagery. We also have that 1851 map here, and this is a really nice 2019 ortho photo data set that was captured by Gary Sundin with the Marine Resources Division. He's been flying this area of Quawah pretty consistently over the past few years. So again, you can use the locate tool if you're out on the beach, and it'll show you, oh wow, I'm here, and the beach used to be way out here. So those are some of the communications tools that we're trying to use to help our managers and volunteers on the ground to help people understand kind of the context of how much erosion has happened and where they are, where they're located. So another project that we've been working on since 2019, this is in conjunction with Archaeology and the College of Charleston, was we went out to the island in May of 2019 and collected 4 vibrocores. They were all about 12 to 13 feet in length. And you can see our locations here. We took 1 vibrocore right next to shell ring number 1, a second one, and a third one. We targeted what we believe to be old beach dune ridges. And then we took a 4th out here on this small hammock island that's midway on down the causeway. So the objective here was really to just try and understand the shallow stratigraphy of the island. So what's its composition, what kind of materials, what kind of grain sizes, what kind of mineralogy were we seeing. And we also took some samples for optically stimulated luminescence dating. So trying to get a handle on how old these sediments are. Maybe the last time Pocky was actually at the shoreline were some estimates that we were trying to make there. So we did this using vibrocoring. So this is sort of a picture of what that looks like out in the field. Here's Sean Taylor and Scott Harris with College Charleston, and Will Dorr, who works in our geology office. And so using a vibrator rig, we used also some 3-inch aluminum piping, and we just drive that down until we hit refusal, and then we put water in the top to create sort of a seal and then pull it back out. So pretty simple technique, definitely effective. And these are what the cores look like when they were split. So definitely a really nice contact between sand layers and then underlying estuarine muds. So at one point in its geologic past, Pocky was formed by sand that was deposited on top of mud. And you can see here that these are the areas that we took for OSL dating. And so OSL dates, we are still sort of hashing through what exactly they mean in the context of the larger coastal landscape, but I can definitely tell you that we're pretty confident they are definitely not Holocene. So they're older than about 11,000 years. So this is going to have implications for trying to understand the evolution of the area and what it may have looked like when the Paleo Native Americans were there constructing shell rings. Another thing we're working on right now is trying to develop a short-term erosion rate. So if you'll remember back a few slides, we talked about how we came up with a long-term erosion rate using imagery from 1949 to 2016, and found that long-term erosion rate was about 7.5 meters per year. Well, it has become evident over the past several years that the erosion at this location has really, really sped up. Our managers on the ground have estimated that it may have been as much as about 75 feet in one particular year. So using some of the UAV imagery that Gary has captured, along with some shorelines from our Office of Coastal Ocean and Coastal Resources Management, we are trying to better understand, so going from 2015 to 2021, how the erosion rate has changed. And just because there's been so much erosion on an annual basis for the last 5 or 6 years. And Gary has really captured that, and these are some comparisons and side-by-sides of UAV imagery. This is one that was captured. So this is all the same location, showing the same location near shell ring number 1. This is November 2017, moving forward to July 2019, and then February 2021. So you can see how this area really thins out between 2017 and 2019. But between 2019 and 2021, it is just an unmistakable amount of loss here. And what's remarkable is that this really wasn't a time during which we saw a lot of tropical cyclone activity. This is another glimpse. This is an area down towards the south of the island, and you can see again 2017 to 2019, and then 2019 to 2021. It just appears that the erosion has really, really sped up in the past few years. So another another thing that we're interested in looking at is trying to figure out why that happens. And I think by looking at the erosion rate on an annual basis, we're going to be able to tease out some of those questions of, is it related? How much of this is caused by tropical cyclones? Anybody who lives on the southeast coast of the US probably knows that, we've had an increased periods of cyclonic activity over the past few years, really starting with Hurricane Joaquin and the associated historical flooding event in October of 2015. Every year since then, with the exception of 2021, we have had impacts from some sort of tropical system, be it Hurricane Matthew, Irma, Dorian. So there really has been an uptick in the number of storms that we've had over the past few years. And prior to that, things were relatively quiet. We also, another interesting facet of this is that we've also seen an increase in the number and the duration of spring perigean high tides, which are also known as king tides. And anecdotally, our land managers at Botany Bay, they say after these spring tide events, which usually last several days, they see just an enormous amount of erosion happening. So this is a dashboard that was put together by the GIS division with the city of Charleston, and they and NOAA are doing a fantastic job of tracking these high king tides, and also putting down, the hours of flood risk. So average high tide in Charleston is about 5.5 feet. So we're really talking about, tides that are causing nuisance flooding in our built environment, but also in our estuarine and coastal systems. So NOAA did a report, and in 1950, they only had 2 of these events every year for a total of 4 hours of flood risk. By 2014, there were 25 events with tides greater than 7 feet and a total of 42 hours at flood risk. And you can see in 2019, we had 86 events, 165.9 hours at flood risk greater than 7 feet. And then in 2020, we had 65 events, 131.6 hours at flood risk, no hurricanes. So this is all just very high tide events, and these are multi-day events. And when they're over, we see a lot of erosion having resulted from these. So this is something that's sort of crept into our consciousness, I'd say, over the past really 5 to 6 years as well. And it's been kind of coincident with this uptick in storm activity. So another project that we have devised recently, and we're actually going to go out and set it up next Tuesday, is using using what we're calling erosional transects, going out onto Pocky and setting up just temporary benchmarks with poles and flagging tape, and just running a tape measure from the back benchmark through the front benchmark to the active beach phase. And we want to do this at these 4 transects. We're hoping to put another one down here on the southern part of the island as well. We're hoping to do this at least quarterly, and we would also like to take measurements before and after as many of these predicted king tide events as we possibly can, to get some numbers on how much erosion is happening, and try and figure out how much of that erosion may be attributable to king tide events. So, and this has implications for, again, the shell rings, understanding how much time, understanding the short-term erosion rate is going to help us understand how much time shell ring number 2 may be, out of danger, and how much time the archaeology team may have to excavate and work on this this shell ring. So I think we're hoping that the improved short-term erosion will help with that. There's also implications for other DNR biologists and managers, people who manage the property, as well as people who research things like loggerhead sea turtle nesting, which has definitely taken a hit from these king tides as well. So research is definitely ongoing, and it's sort of exciting because it's definitely fast-paced and interdisciplinary. And so some of the things that we've learned over the past 4 years are, again, that coastal areas of South Carolina experience highly place-based specific conditions. Something that's happening on an adjacent island can be completely different than what's happening on the island directly to the south. Also, conditions can change quickly. I think we saw that, you know, in 2015. Really, it's kind of like a switch flipped, and we saw more storm activity as well as more of these high king tide events. So that really necessitates flexibility and also just bringing in different groups of people for outreach, for their expertise, and communication with local stakeholders, educators, and members of the public is really critical. It's sort of where we started when we began work out at PACI, and I think it's still really, really important. A lot of people are pretty, you know, invested in the property, and people love going out there and want to know why things are happening and what's going on. So it continues to be just a very dynamic place to do research. So with that, I'd like to acknowledge and thank a lot of people who support this work. Denise Sanger and Blake Kepler with the ACE Basin near, Bess Kellett with Botany Bay Plantation WMA. We received some funding through our South Carolina DNR Harry Hampton Wildlife Memorial Fund. Also like to thank the LWC archaeology team, my coworkers with the South Carolina Geological Survey, Scott Harris with College of Charleston, and Jessica Boynton with OCRM, and then finally Gary Sundin and Evan Cook with the Marine Resources Division at South Carolina DNR, who are doing a lot of on the ground work with surveying and flying UAVs and capturing imagery for this area. And big thank you to Meg for inviting me to talk today, and to all of you for having me here this morning. Really enjoyed the chance to present to you, and I would be more than glad to take any questions that you have.